Greetings once again. My name is John Gabriel, and this is a new calculus channel. And today I'll be talking about how you can understand related rates. So let's begin. So, related rates are part of any normal calculus syllabus or curriculum. And unfortunately, the majority of teachers don't really understand what it's all about, and although they acquire some skill and know what to look for in solving the problems, their understanding is very superficial. So one can only wonder how they expect their students to acquire a good understanding. And honestly, to me, it's a mystery because it's impossible. And I know that what I'm saying is correct because I've taught many students and I've spoken to many students who have been taught by mainstream teachers, and they really don't know what they're doing. And I'm about to show you why they don't. So I've chosen a random problem from the internet, and you're looking at it in front of you. Very quickly, it says a leaky water tank is shaped like an upside down cone, and the tank is 4 meters high, and the base has a radius of 2 meters, and the water leaks out at a rate of 0.15 cubic meters per second. At what rate is the height of the water in the tank dropping when the water is 0.7 meters deep? Okay, so this question tests quite a few competencies, and one needs to know some geometry. For example, similar triangles. So to be able to express r in terms of h, you need to understand the theory of similar triangles. And of course, besides the normal uses in problems like this, remember that the theory of similar triangles is what is used to derive all the theory of fractions and arithmetic operations and how algebra is established. So it's very important. And then the next thing one needs to do is using the constant rate. And it's important to stress that this 0.15 cubic meters per second is a constant rate, okay? Must be a constant rate, which the water leaks out of the cone. So that means that dv dt is, oh, and there's a mistake there. That should be m cubed. No. Well, there you go. I'll fix it later. So teachers should avoid calling these rates as rates of change or instantaneous rates because they do not change, number one, and they have nothing to do with a given instant. And of course, there are different rates, but they're not changing, okay? And those two things are not the same. Different rates are not the same as changing rates. And of course, a rate is never anything more than a number or a number that describes the tangent line slope at a point of a given function, smooth function. Remember, if you don't have a smooth function in calculus, you can't use calculus. You can just toss it out the window. You need smooth functions. So the slopes or rates, dv dt and dh dt, are related by the volume function. Okay, so you have volume is 1 over 12 pi h cubed, right? And so if you differentiate both sides, you'll end up with what you see here on the right, this expression here. And so this here is the relation between the two rates. Their product is equal to pi h squared over 4. And if you substitute 0.7 meters in the slope function, then you have 0.389 cubic meters per second, which is the rate at which the water is leaking. And again, there I left out the cubic meters. Never mind, another thing to fix. So contrary to what those fools, Neil and Chouard, would have you believe, the expression dv dt times dt dh is treated exactly as one would treat a function, okay? I mean a fraction, and it is equal to dv over dh. Now, you'll recall that according to one of the books these fools wrote, they said dy dx must at least for some considerable time be regarded as an inseparable whole. I wonder how much time that is. You know, I mean, it's so ridiculous. Is it 1 second? Is it 2 seconds? Is it 1000 milliseconds. It's absolute garbage, just as delta x is, and it does not in any simple or straightforward way mean anything like dy divided by dx. Well, it means dy over dx, and it's exactly a fraction. And of course, this statement, contrary to what they think, is not gibberish. What they write is gibberish. So a derivative is a fraction of differentials, okay? So if dy over dx is a derivative, the differentials are dy and dx. And the differentials are symbolic numbers, and the fraction is a symbolic fraction. And it has nothing to do with the nonsense of infinitesimals or limits. It's exactly a number. So dh dt is a simple differential equation and has the solution. Therefore, the rate or the slope in this, it's always anything that you see called rate always relates to the slope of the function, at which the water level in the tank is dropping when the water is 0.7 deep is so many cubic meters per second. And one can find a slope or a rate function that will produce the given rate of water at any water level, okay, given that dv over dt is constant. So for example, if we didn't know the function, we could just plot the, let me just do this here. We could just plot the trace. So if we plot the trace, so we could say, okay, let's plot the trace. So it'll look something like that. And of course, it turns out that this function is in fact what you see in front here. Okay, so this is the slope function. And of course, this here is its solution, all right? And you can put in any water level you like here, and it will give you the rate or the slope. So let's go over a few things first. The formula does not give you a snapshot of the problem as they tell you in that random example or at one instant of time. In fact, that's gibberish. It has absolutely nothing to do with time whatsoever, okay? There's nothing involving time. It's just a rate that was given to you, and you don't know what the function is with respect to time. So taking the derivative of both sides with respect to time has nothing to do with time moving forward. Another silly expression used in the random example. And in fact, the problem does not provide a time function for either the volume or the height, even though the time function is implied by taking the derivatives of both the volume and the height with respect to time. And finally, it's not necessary to change the sign of dv to dt to a negative unless it will affect a subsequent operation. In this case, it doesn't, so you don't have to change it. That is finding an integral or using it in another formula. So it was given in the problem that dv dt represents a loss of water. In other words, it's leaking. So if you're a teacher, you can learn a lot from this. And if you're a student, you can learn more than your teacher, because your teachers, obviously, most of them don't know these things. If you're not already a subscriber, become one. Tell your friends about this channel. Donate at my GoFundMe link, which I'll place in the details section. And who knows, hopefully in the not too distant future, I'll come up with something else that you can use practically in your mathematics studies or calculus studies, or if you're a teacher,